In this video, we'll break down a high-concurrency system design problem where an API is used to capture votes from users, but must process them without timeouts, data loss, or scaling options. Problem context. You are designing a voting API that receives high-concurrency requests from users voting via mobile devices, has strict constraints, only one database connection, only one application instance, no scaling out. Must not lose any votes. Must not time out or reject requests under load. Design objective. Design an architecture that accepts votes from any number of concurrent users, saves all votes to the database using only one connection, prevents request failures, timeouts, or data loss. Solution approach: decouple input from processing. This design is based on a message-driven architecture, where the ingestion API is decoupled from the processing DB writes. 1. Asynchronous processing with in-memory queue. As soon as a user sends a vote, the API immediately acknowledges the request by adding the vote data to a thread-safe in-memory queue, such as a blocking queue or a concurrent linked queue. This makes the request processing non-blocking, allowing the server to handle a large number of requests without waiting for the DB. Think of the queue as a temporary holding area for votes. 2. Single background worker for DB writes. A single background worker thread or a lightweight polling loop runs inside the same application. It pulls votes from the queue one at a time or in small batches and writes them to the database using the only available DB connection. This ensures that no concurrent DB operations are attempted, satisfying the single connection constraint. This is analogous to a consumer process in the producer-consumer pattern. 3. Batching optional optimization. The background worker can group multiple votes into a batch and insert them into the DB in one transaction. This reduces I/O overhead and improves efficiency. Still, all writes go through the same DB connection. 4. What happens under load? The API continues to accept votes, pushing them into the queue. Even if the DB is slow or temporarily unavailable, votes pile up in memory, not lost. Once DB becomes available, the background worker drains the queue gradually. This is the essence of backpressure management. Don't block the user-facing service. 5. Handling crashes or restarts. Durability, optional. Since memory is volatile, to avoid vote loss, you could persist votes to disk before adding them to the in-memory queue. On application restart, load the pending votes and reprocess them. This is called a write-ahead log, WAL, or persistent queuing pattern. Alternatives: use embedded durable queue libraries, like Chronicle Queue, LMDB. Integrate external queues, Kafka, RabbitMQ. But your scenario disallows external infra. Underlying concepts and design principles. 1. Producer-consumer pattern. API acts as the producer. Background DB writer is the consumer. Queue acts as a buffer between them. 2. Decoupling. Input, API layer, is decoupled from processing, DB. Avoids tightly coupling request flow to slow database operations. 3. Asynchronous architecture. User doesn't wait for vote to hit DB. Vote persistence happens asynchronously, maintaining responsiveness. 4. Single responsibility and isolation. API layer focuses only on accepting input. DB layer focuses only on reliable storage using the one connection. 5. Backpressure management. Queue absorbs high load. System doesn't fail under pressure. It slows down processing instead of rejecting input. What you cannot do, due to constraints: you cannot scale horizontally, add more app instances. You cannot open multiple DB connections. You cannot directly call DB from every request, as it will serialize and time out. Benefits of this design: scalable on input, handles 1 or 10,000 concurrent users, reliable, No data loss if queue is persistent. Simple and efficient. No complex infra required. No timeouts. Users don't wait for DB operations. Summary. Component. Role. REST API. Accepts votes, places them into queue. In-memory queue. Buffers votes, prevents API from waiting. Background worker. Dequeues votes and writes to DB using single connection. Optional durability. Write votes to disk before queue to prevent memory loss. Subscribe for more system design and back-end architecture tutorials.